So we made sure that the optimizer works, and we tested the optimizer, and our RNN is able to learn. And the last thing we have to do is to arrange it nicely and create a package where we have the option to train the RNN. And I will say a few things about that. And where we have an option to apply the RNN to new data. And that's the topic of the last chapter. We want to create a full package. So we have an RNN that works, and we want to also create plots, of course. So that's what we did already. So therefore, we want to import matplotlib, of course, and we want to set up a function we just call runMyRNN. And in this function, we want to have x, t, and yt as an input argument. Then also we want to keep the activation function as an input argument, which is an option we want to keep. And then also other things like the learning parameters, learning rate, decay, and momentum. And then we essentially can just copy and paste what we had from our test script already. And so this part where we just initialize the RNN, the optimizer, where we initialize the monitor, and while it's running, we also want the user to give some feedback. So it's always nice to do something like that, saying the RNN is running, so that everyone knows, okay, it's doing something. So I don't see a plot yet, not because something went wrong. It's really running. Yeah, and then we just copy and paste the loop that we have already. And then, of course, we also want to create a plot. And we also want to create a plot from the monitor. And also we want to give a message, okay, type a message, that's the final MSSE, and the job is done, so the RNN is done. And in particular, we want to return the RNN now, because the RNN now contains the updated weights, all the updated learnables, and we're going to need that, of course, for the application of the RNN. So this will be the training part. And then we use the result for applying the RNN to a new data set. So this is the first part, and therefore, before we continue with the second part, let's actually implement the first part. And as usual, I would recommend to create a new folder, and let's call it full package. So we also want to navigate to the folder. So full package, and also save everything in the new folder. So let's start with the RNN. And also with our script. So everything has been saved now. And now we just set up or create a new function in our RNN. So we do not create this as a class. We just set up a new function directly. So maybe you should also divide it here. And first of all, you want to create a plot. So we just import a matplotlib. So we have that already here. And we call it run my RNN. And that's the training part. And for the application part, we just want to call it, apply my ANN. So we can actually copy and paste already those parameters. So we had good experience with a certain learning rate, also with a momentum and a decay. So we can actually keep those parameters as default parameters. And we want to have, of course, xt and yt as input. So xt is our input, and YT is the comparisons or for our evaluation for the training data. Then we also want to be free of the activations. So the activation, what else do we need? We need the number of epochs. And let's say, yeah, 200 was pretty sufficient already. Let's set 400 just to make sure. And the number of neurons. So we had 500, let's say 500 as well. And then it's also had 500 epochs. So just to show, yeah, we had 500. So then we have a reasonable number. So the number of epochs, the number of neurons, and then we want to continue with the learning parameters. So, and then we just do exactly what we're doing here. We just copy and paste this part. So we can just go there and copy and paste. And we don't need self RNN because it's already defined as class here, and we don't use it within the class. So we can just directly say RNN. Then this will be our activation function here. Then, of course, the learning rate and the momentum is what we get from the input and the decay as well. We need this. We don't need this anymore. Then the number of epochs. And then before it does anything else, just tell the user that it's running. So we just say print RNN is running. Yeah, and then we have our loop with the number of epochs. That does the job already. And at the end, we want to have the final plot. And after the plot, we also want to just plot L or print L. So we just turn L into float again. And then we can just say print. Let's use full string because I want to print L, so the loss with 3 digits. So we say done. And then MSSE equals, and we want to give L as float number. And that should give us the 3 digits then. And then we return our RNN. So that's something we can already test. So let me just do that. So we don't need this part anymore. So all of that is not needed anymore. Also, well, we still need this. Well, actually, we can use the default values. So let's just use the default values. So we import our RNN. And in the RNN, there's also run my RNN. We have XT, we have YT. Activation is then the tangents hyperbolicus. And it should return our RNN. Okay, so let's run it. some space here. And now let's run it. It's running, so that's the first plot. And let's wait for a few more plots and to convince ourselves that it's running. So we have the default values, the ones that worked the last time. So we have 500 neurons, we have 500 epochs, and don't worry why it's relatively slow in my case, because my computer is running Zoom in the meantime in 2 monitors. It's just normal that it takes a bit longer. So it's doing something, and let's see what we get. Right. So I've tried a few configurations of our learning parameter. So yeah, I also played with the decay equals 0. Number of epochs was 500. Number of neurons was 400. So I did some test runs. And in case you have used the same parameter, you also should have gotten the same plots, more or less. So the MSSE dropped down to 0.03, so 3%. Doesn't get a lot better because we have the random noise, of course. And then the fit at the end was pretty successful. So we now have a well-trained RNN, and now we should be able to apply the RNN. So let me just go back to the PowerPoint. So we created the training part, and it returns the RNN, and we can use it now for a new data set. So we have our, so we should, after a few hundred epochs or so, so if you run it up to 1000, you should have a result that looks like that. Okay, so but now we also want to apply the RNN to new training data. And when we have a new data set, XT, we just take the RNN as an input because it contains now the rates which have been modified according to the loss function. And the only thing that we have to do now is running the RNN cell, which is the forward part. So we just have to call the cell based on the RNN, and it will create prediction y hat. So we just run the forward part only. And of course, we want to plot that. So that's the next part, and that's almost the final part. So we can now apply the RNN to new data and want to see how well it actually works. So just because of the structure of the RNN cell, so we're going to need HT as an input, which is just 0. So we can just take the age from the RNN, and if we want to keep track of age, we can also just use the list of all these vectors, age of t, as an input argument, and then also can keep track of age if you want that. But since we know our RNN works, we don't have this as an output argument here, so we're only interested in y hat. But just imagine you still want to keep track of the states, you can still do that. And then, of course, we want to return y hat, and then we also want to plot it. So the next step is just to include the part in the code where we can apply our RNN. This will be a new function. So we should probably just have another separator here, or divider. So we just say definition, and then apply my ANN, which I'm gonna do here. So that's actually from the previous one. So let me just remove it so that you see it's all live. Okay, so we have the definition of apply my RNN. So the input will be the new XT. that will be the RNN itself, because it has the weights, so the learnables adjusted to the loss function as the memories. We still need T. So and this time it's not T from the RNN, because this time it's T from the new data set. So we just say max X T shape. And then we have Y hat. So we want to reallocate the matrix for Y hat. And we could just do this with NP zeros. Again, with a certain size T times 1. Then we just want to get the initial value for H, because we want to call the RNN cell, which needs it as an input. So HT is just the initial value, H0. And in principle, we can now use H for rewriting H from the current data set. But of course, the length of H does not correspond to the length of XT. So let's rather set up a new one. And let's say just H equals NP0. So we can actually copy and paste that part here. So that's the number of neurons, which is in the RNN. And then T is the T of the new data set. So that's not the T we used for training, because we might have trained with a different data set. And now we want to make predictions from a new data set. So that's why it doesn't have the same size, of course. And then we call our RNN cell. And the input of the RNN cell is just this. So we need XT. We have XT already. We need HT. That's what we have here, the initial value. We need the activation function, which is in the RNN. Because we also need the memory of the, well, actually we don't need the memory of the activation function, but of course we need the same activation function. And then we have Y hat, where we will calculate the values from. And we want to have Y hat being returned from the cell. So we don't need those these output arguments here. That's why we have the underscore. So then we don't get the output arguments. They're not provided as an output argument, so it also saves time if we just use the underscore here. And then we can also just plot Y hat. So let me just copy and paste this part here. So we have our XT, and then we want to plot XT versus Y hat. We don't need this part. And of course, we also want to return Y hat. All right, so we have now two parts. We have the part where we train our RNN, and it returns the RNN with all the weights. And when we want to apply it, we have a new XT, and then we just go through the forward part. And what is the forward part? It's just running the RNN cell. And then we just want to plot the result and also return Y hat. Okay, so, and then we want to test this. So we just run our RNN. So that's what we did already. So we have RNN already as an input. And then we create a new X. So let's call it X new. And also choose also different sizes of the increment. So for example, for the training data, we had 0.1, but it also doesn't have to be the same increment. So we can choose 0.3. So let's really use a different one. Then also let's reshape it and then apply it to the RNN. And then let's take a look at Y hat. So we go back to the part of the script where we test our RNN. So we have the RNN here now. So we still have to import this because now we have to apply our RNN. So we create, so we have our RNN here already. So this is what we have done, what we have trained already. So we have the RNN with all the weights and all the D weights. And just to make sure, here it is. So now we want to apply a new data set. And let's call it then X underscore new. And really, let's pick different values. Let's say from 0 to 20 so that they overlap a bit, because then we have a direct comparison of the training data, and also really just choose a different increment. And let's also rearrange this. And now we can call apply my RNN, which has X new as input. The RNN that we have here already that's been trained, and it creates Y hat as output. So this is Y hat, and let's see what Y hat is. And it creates the plot. Well, let's create a plot with Y hat. So let's just copy and paste this part here. And let's try to create this out, this plot here. Maybe it looks a bit better now. So we have Y hat. So XT versus YT, XT new versus Y hat. And let's see what it looks like. So that actually looks pretty disappointing. So the fit went well, and we could argue, well, maybe we haven't run it long enough. So how many epochs was it? In my case, just 500 epochs, but the fit is already pretty good. So even if I run it like 10 times longer, the fit would improve, of course, but not a lot. So that's probably not the point. That's not the reason. And apparently it also fits the training data pretty good. But then when it comes to new data sets, it doesn't really look very convincing. So let me just summarize this. So we tested this. That's after the fit. And here I just did it for 3,000 epochs. You see the MSSE is like 1% or something. Before that was like 5% or 4%. So it doesn't really improve a lot if you run it for 1,000, 2,000, 3,000 epochs. And then you get something like that. And that's really disappointing. So even if you run it for 3,000 epochs, kind of see that it understands the periodic behavior, but it's not really what we expected. So what went wrong? And The reason why it doesn't work is, so in principle, if we have a more sophisticated network, it would be able to solve this problem to predict from xt to yt. So what people do in practice is actually something else. So xt, in a sense, is actually doesn't really matter concerning the prediction of yt, because you know what yt looks like in the past. So why not just using yt and try to use it as training data if you just shift it by a time step dt, and then map instead from xt to yt, try to train a network to go from yt to yt plus dt. So your new xt is just yt itself. Then your training data is the same yt, but you just shift it so that the training data is the overlap of the shifted version with the actual version of yt. And then you can also check what is the surplus here, or the overlap here, or the extent. What's the extent here? That's the validation data. So you can also check how well the prediction works based on the DT part, which is not part in the training. So you can directly use it as validation data. And then what comes next is the prediction. So you do it actually in a slightly different way. And we want to implement this now in our package and see what the result will be. So hopefully, and may I tell you, it will be a lot better result, but we want to keep both options, just that you can play around with the RNN a bit. So we want to still keep the option that we have X as an input and Y as an input, but we also want to keep the option that we have Y and YT plus DT as an input, so that we really can compare it. So let's try that and let's implement this. Another thing is, if the sequence is even longer, but we're not going to implement this in this case, you also just do this with a randomly chosen subsample. So you just select a random subsample and then just do this for different subsamples in the actual time series. So it's a bit like calling mini batches if you, for example, do image analysis, because all the images are too many. So you just call subsamples the mini batches. So it's the same idea. So that you run a few iterations over the mini batches and call it the next mini batch and so on. So this is something we will do in the course about LSTMs, but not in this case, but we will keep this in mind. So let's try to fix that, and let's figure out how to modify this package. So how are we going to do that? So we have everything that we need. We just need to rearrange it a bit. And there are a few reasons why we want to do that. So first of all, we want to do the following. So first of all, we need DT as an input. That's the time shift. And for example, if we want to just map XT on YT, then our DT would be 0. That's why we leave it as a default. However, if we want to map YT on YT plus DT, then our XT is actually the YT. Our YT is also YT, but then we have to implement our shift DT. And we also want to choose how often do we want to see a plot while it's generating the plot, just to make sure that it really does the right thing. There's another thing that we want to change, is that we don't want to have XT as an input when we initialize the RNN. The reason is that we also want to prepare for the next lecture, where we want to create an LSTM from scratch. And in this case, we want to call these different batches. And therefore, XT will always be a randomly chosen chunk, so to say, from the data. And it's always a different one. So we choose it randomly, and that's why we don't want to have it when we initialize the RNN. So we have to apply a few minor changes. And therefore, we don't have T as an attribute in the RNN yet. So we just have to determine T. And now we have to do the following. So if dt is not 0, so if we want to really map yt to yt plus dt, then of course we have to cut it out accordingly. So we just do exactly this. And then we just train the overlap. And let's call it x underscore, so xt underscore dt and yt underscore dt. And then also we need to plot x in a different way if you just want to plot both together then. And if dt is 0, then just leave it as it is. So let's first of all include this before we continue with more. So we just go to our run my RNN. Then we add one more thing. So we just say, maybe I make a line break. So we'd say plot each, let's say every 50, because we had already good results after, what was it? Yeah, like 500 epochs. So we just get 10 plots. And the default value for dt equals 0. Then we also want to remove this. And of course, we have to modify this part in as well. So then t is not an attribute of the RNN, so we have to measure t. And so t is then just max xt shape. And now if we want to choose mapping xt on yt on yt plus dt, we still need an x value to plot. So we just create x underscore plot, which we can just do with np arrange. So that's then actually that's not actual time. So that's just, for example, if this is time series, that's not actual time. That's like the pseudo time just to plot it. So for every step, we just plot it. So let's say we this np range from 0 to t. Okay, and then we have to say if we have a dt, so if dt is not 0, so you can also say if dt, but let's say if dt is not 0. Then we want to first of all create an x dt. And if we have this shift, we want to learn yt from the future. So we just take yt and just cut it accordingly. So from 0 to minus dt. So that's how you cut off the end, which has the size dt. Probably can show you that. So for example, you have, let's say, test equals np arrange, I don't know, from 0 to 100. So then we have all the values from 0 to 100. And then if you just say test, and I want all of these values minus the last 15, yeah, that's true. It's only one vector. Then I just remove the rest here, right? The last 15. And that's what we want to do here. So the last dt we want to remove. So then we have this as a training. So this is the x value then, and as a y value. So yt underscore dt is then the other part of the data. So just from dt upwards. So just to again show you the example. So we would just then start from dt and the other one, and then from there upwards. So we are always like 15 ahead. So this predicts this and so on. So, and then for plotting reasons, you will see later, we have to do this with xplot as well. So let's call it xplots with an s equals xplot, and then we just cut it out for the same reason. Because we want to plot these different data, different vectors containing the data of the different shifts. And if not, kind of still want to be consistent with our variables. So then we just want to map xt on yt. So this is just xtt, and this is just ydt. And also this part just stays. Oh yeah, just we keep just stays as it is. Then of course we have to change the names here. So we just go on and then say, of course, well, this is then just yt underscore tt. But then, of course, it comes from x underscore tdt. So we don't want to also monitor now because we know it works. So we also want to remove that. And yeah, we just change the names here. So let's also go back to the screen. So now we also want to put xt in the forward part. So again, we need to go to our RNN itself to modify this. It would not work yet. And then we want to compare this xtdt to ytdt. Depending on what dt is, it's mapping yt on ytt or xt or yt. Okay, so we don't need it here. Then we have the backward part. We want to keep this part, but we want to do this after the optimization part, and we don't need this part here. Okay. How else do we want to proceed? So of course, we also want to we still want to create a plot, and we still want to see how our prediction works during the different epochs. So how does it optimize and whether it goes in the right way. So we now create a plot, and we want to create a plot with the entire xt. So during the optimization process, it always updates the weights. But we want to, every 50th plot or so, we want to create a plot of the prediction from the entire xt and want to plot this. So we want to plot the data, and we want to plot the prediction from the entire xt, which creates an y hat. And of course, it's a prediction with dt. So xplot has to be added. There has to be added dt to xplot. So we want to, first of all, create a plot that shows the entire data set plus our current prediction. and with the applied shift in x because y is trained in the way that's the prediction with the time shift dt. And we want to also, of course, plot L. And what we also want to do is we want to create a nice plot, which is, so this part is a bit technical, where we have a bar, so a vertical bar showing us from where the prediction actually starts, so that we really have an idea throughout this optimization process how well the optimization takes place. So we just create a bar, so a bar plot, or which is where we plot a bar and vertical bar, and after this bar, we want to fill it with gray, so we have the color black, but with an alpha 0.1, so that really see when we use our code. Okay, this is the part that is prediction, and then let's see how well that works. And in our training data, since it's a sinusoidal behavior, then we immediately see whether this prediction makes sense or not. So this is the technical part. This is not necessary for the code, but it's just nice to see how, if the code works and how well it works. So therefore, let me just implement this. So I still want to show how that works. So if not n, so that's the number of epochs, and if we divide it by the number of plots each, and there's no rest, we want to see the plot. So we just say plot each. Then we want to run the forward part with the entire data. So not only with the DT part. So we want to then plot xplot versus the actual YT. And then we want to plot RNN head, which is been generated immediately from the forward, if it passes through the forward part. So we can just use RNN head, and then we just shift xplot by dt. All right, and then we just add this technical part. And so I want to be, so we just add this technical part, and yeah, as I said, it's pretty technical, so I just want to spare you that because it's just the plotting, just show you the code, of course. And you can just copy and paste it from the GitHub repository if you like. But you will see later that creating such a plot makes sense, so I just add it here. So we create this plot. So we plot X and Y. Then we have the label. Then we have the title. And then we just put this all into one plot. So if this equals is not 0, then we want to draw this line here. And this line goes from minus, so from lowercase m to capital M. So we also have to calculate this first. So let's do that here before we create the plot. So we just calculate the maximum from RNN head, a Y head from the RNN and YT, and the minimum, and then we just draw this line. Okay. So we also want to print the current value of L once we have the plot. And then, of course, that's the current MSSE. And of course, we need to calculate L. So what was L? So L is, of course, the dot product. So L is 0.5 times NP dot of dy, which we calculate all the time. So this is just dy times dy divided by t, but if there's a phase shift or a shift in time, is t minus dt, because that's the overlap then. So otherwise we would underestimate L. So let me just take a look at the code where that makes sense. So we have L, this makes sense. That should also work. So that just plots this line that creates a shade in this area, and you will see that. Okay, so we are almost done, because there's one more thing we want to do. Let me just show this in the slides. So once we're done with all those plotting here, we still want to create a plot at the end, a final plot, so to say, and again with the entire data set. So we again want to calculate, so we want to run x underscore t through the entire network, and then create a plot after the network is done with the training part. So that's the final plot, so to say. So therefore, let's go back and kind of just copy and paste what we have here. So we can actually keep this part. And now we just take the RNN. So we also don't need the monitor here anymore. And whatever the final input is, or whatever the complete input is, so we just want to run it after the training. We of course want to run it again through our network and create a last final plot. Why? Because it might be that plot each. So for example, if we have every 50th plot, but we have, I don't know, 255 iterations or epochs, then we gonna miss the last 5 ones. So we really want to see the final result, and that's why we want to include this here again. So we go through the forward part, then that generates y hat, and again, if dt equals or does not equal 0, or you can also use if not, then you have dy, and this is RNN y hat. So this is just RNN y hat. Okay, but we have to calculate the difference between y hat and the actual y t. And remember, we have this phase shift here. So this goes from the first value to minus dt. And this goes the other way around. Because that's what we wanted to train for, right? So this is our input data, which is just a phase shift of y hat. And we want to compare the phase shift of yt, and we want to compare it to yt in the future, which is shifted by tt. So that's why we have to make this, have to apply this shift here. And then else, we just keep it as it is. And also this is a capital Y, so that we are consistent. And then we have the final dy. So we can also calculate the final L. So we can also print the final L. So we have the final L, but we also want to create this plot one last time. And that's what we're also going to do now. So we just copy and paste this part and create this plot. So we just go and copy and paste this here. Maybe you should also write a note. So one final plot. And we need to shift this here to the left. And now we create the last final plot. So we just plot x plot versus yt. Then of course the y hat, but with the phase shift dt. Then we have the label here. Then we can keep this part. And then we also keep this part. All right, so that would not run. So we'll get an error message. And why do we get an error message? We still have to perform one or two more steps. So the thing is, we removed xt in the init part for some reason. And that's why we don't have xt here. And therefore, of course, everything that has to do with t is also not possible here anymore. So we have to remove that. And we just copy and paste that. And also we have to remove this part here. And we just put it into the forward part, and the forward part has xt now as an input. And therefore we can just copy and paste the part we had in the init. So, and then we can also test our package. So this is the last step that we have to perform. So we just go to our RNN, then we remove this part here. And we just copy and paste this part. And we just do it here. So we just include it here. And then we have our xt. We still get an error message here because there's no t. So we also remove that and also put it in here. So again, I want to explain what the reason is. So before it was easier just to do it this way. But now if we, for example, decide later that we want to cut out just random parts of our time series here, then we always have different parts that we feed into this forward part. So here, for example, we can just cutting out mini batches, so to say, so like random parts of our sequence and feed them inside here. So therefore, every time we run this forward part in the epoch, and we will do this later than in the other lecture or many iterations, then we will have a different part of the time series in the forward part. So it makes more sense now to include it here. In principle, we could have done that earlier, the same with the cell. So creating the cell earlier if we knew already what the structure will be. But I just also wanted to show you, of course, how to do this step by step and how you have to modify this then accordingly if you just change the requirements. So we now have everything that we need. So we have xt here as an input, not for the init. Then we have we can determine t. When we have t, we can determine y hat and so on. Okay, so let's now test it. So let me just run it. And let's hope there's no error message. So let me just run it again, just the old method first, and then let's try the new method. So it's running. And let's see, and I will run a few tests. You see the initial values were completely off, so let's hope that it kind of worked. So let me just test run this a bit. And so at least there's no error message. Yeah, let's see what we get. All right, so first of all, we should see a plot every 50 iterations, and yeah, it was looked pretty good. 1% error. And again, we have the same result, which is not really satisfying. So that was, so to say, the old way. And let's do it the new way. So we still get the same result, of course. But now, let's try the new way. So, and so it was actually relatively slow. It's inefficient and it's poor performance. So that doesn't really work. So let's try now to use YT. What are we going to do now? So let's also try with fewer neurons. So we had like 500 neurons. Now let's try it with 100. And now we implement the phase shift dt. And then our xt is our yt because it takes care of that internally. And then we apply our ANN that creates the prediction for y hat. And then we just want to plot, first of all, again, xt versus yt, but then we also want to plot x underscore t plus dt and versus y hat. And then we actually should see the prediction. So let's see what we get. So let's run this. So we can actually just keep the structure as it is. The only thing that we have to change is say, okay, we have a dt, and let's say the dt is 50 time steps in the future. So we want to make a prediction with 50 time steps in the future. And then we just run our RNN. So we can also copy and paste the import just to make sure it works. And then we have yt. And there's also one thing we could actually do. So we can keep the tangents hyperbolic. Well, let's keep that. And then we have the number of epochs and number of neurons. So let's say an epoch. Let's actually, yeah, do something moderate again, like 800 epochs. Let's start with only 100 neurons. Remember, we had 500 neurons here and 500 epochs, and the result was actually not very sufficient. Yeah, and we just keep all those values that we have. Decay is 0. Well, let's try another decay value. I guess you know that I've been trying this already earlier. So these are these values. Then we have our dt that we need. And of course, that has to be an input as well. So dt equals dt. Now the default value is 0. Okay, so then we apply our RNN to our x new, which is yt. So this is just, so maybe we can copy and paste this here, just to make it clear. So this is from going from xt to yt, and that didn't really work well. So that was not really nice. So, and now the next idea is to go from yt to yt plus dt. So then we run our code, then we create, it calculates y hat, and then we also just want to plot y hat. So we just say, okay, our xt doesn't have any real time meaning, so to say, so we can just set up xt with np range. Which goes from just the length of yt. So then we just plot xt versus yt, and y hat, of course, is the prediction in the future. So we can use the same xt plus, but plus the dt. And hopefully this will give us a nice prediction into the future. So let me just run it. So let's run this part first. And now you see what I meant with the plot. You also see kind of what happened. Let me just check. Let's stop. So that's first of all what I meant with the plot, that we really see where the prediction goes. And you also saw it actually went quite well. But then, yeah, exploding gradient problem. So that actually can happen. So we have to rerun it again. And you see how efficient it actually is. It's a lot faster. So we have only 100 neurons instead of 500. And prediction looks actually pretty nice. And after 150 epochs. So let me just rerun that and just hope that this time it works. And if not, we just have to modify some of the learning parameters. But it looks pretty stable now. It's not perfect, but let's see whether we get an idea. So now we create y hat and create the plot. And well, that's one thing we need to modify later. So let me just remove that. Let's create a plot again. And that's not so bad. So that actually looks pretty good. So let us just try this now for a few more for a larger time shift, and let's take a look at the prediction. We also want to play a bit with the noise. So maybe we add some noise. Also, we want to add a long-term trend. So let's see what we get then, and let's try that. So let me first remove this plot here that we don't need anymore. That was the ugly plot you saw earlier because it's not applicable now. And now let's try to increase dt. So that was just one period. Let's say we can do this for, let's say 80 or so. Now we see, okay, it found already this, and it's again a relatively accurate prediction. Let's see how far we can push it. So we are pretty brave now. Let's say 120. Because the thing is, then you have less overlap, so it should actually get less accurate. But in our case, we have a pretty reliable function. It's just it's a sinus, so that's actually not really hard to do. But you see, it's actually not so bad. And let's now add some noise. Or we have noise. Let's add something like NP exponential, so like a slow exponential growth. So for example, let's say just xt times 0.5. So we just have to take a look at the plot. So let me just remove this here. Let's take a look at the plot. Well, it's a bit too much. So let me just flatten this also a bit. So we don't want to jinx it too much. So let's, for example, that's still too large. So the exponential is always tricky. Yeah, something like that. So that we have a gradual change, and maybe even a bit larger, so that we kind of want to challenge the network a bit. So how does it work, or how does it cope with such a change? So something like that, for example, because that looks a bit unpredictable. So let's try that, and let's go back to 50, and let's see how it copes with that. So you see, it kind of struggles, but maybe it was just bad luck, like at the first try. So let's do it again. So it has a problem with those long-term changes. So let me again just change that here, that you see the difference. So there's almost no trend. You can't really see any trend. And also let's go with 120 again, so that you see the result. As you see, it's not perfect because we also haven't optimized the learning parameters, but you see, well, it does a lot, so it works a lot better now. So it's a lot faster. And you saw also now in the epochs in between, it tries to understand a bit like where does the trend come from? But if it's a very strong trend, it can't really work with that. So, but it works. So for this kind of data, it works. For these long-term trends, we have to think about something else. So it can't cope with those things. And this is where we want to talk about an LSTM and want to implement an LSTM. And you will see then later that the LSTM performs a lot better. But our RNN works, and therefore let me just find some final remarks for our RNN. So let me just go back to the PowerPoint and find just make some remarks. So with fewer neurons, like a lot, and only after a few epochs, we have a relatively good result. So we have a very acceptable result. And if we train from YT to YT plus delta T, and that's how it's really been done. We still had some problems with the with a long-term trend, but this is what we can fix with an LSTM. But first of all, our RNN seems to work, so it's relatively simple. So later when we talk about an LSTM, you will see that it's a bit more complex. So the RNN is very simple and it can be implemented easily. And it also helps to understand more complicated and more complex architectures. So for example, when we want to create an LSTM in the next lecture, we're going to start from our RNN cell. And the RNNs, however, suffer from exploding and vanishing gradient. So that's what you have seen in a few examples, and that makes the training a bit challenging. So what people do is they use NP clip sometimes. We haven't implemented that. And it also fails for long sequences. So that's something you can test once you have the code now. And the problem is all those operations in the backpropagation through time, they have to be done subsequently because there's the error of time. So they can't be parallelized. That makes the whole thing relatively slow. And of course, other prediction methods outperform RNNs. So for example, LSTMs, and especially LSTMs will then just solve the problem of these long-term trends. And if you really want to do one more step, for example, really working with language, with natural language processing, then you have to implement more context. So something like that's called self-attention, cross-attention. And there are other things that you have to take into account. But it's kind of the first step. And therefore, we are done with the RNNs. And if you like, then we can also create an LSTM together.